To wrap up the class, we're going to actually go back to something that we talked about on the very first day, which is how we defined what it meant for something to be a mathematical statement or a proposition. We discussed very early on that every mathematical statement or proposition must be either true or false, even if the truth value is unknown because no proof has been found and no counterexample has been found, right? We gave Goldbach's conjecture that every even number greater than 2 can be expressed as a sum of 2 primes. It's a mathematical statement which must be either true or false, but that no one has proved it and no one has disproved it yet. Now, one thing that's maybe worth mentioning is that throughout the class, the logical foundation that we've been developing to help us decide whether something is true or false, right? So this foundation included truth tables and rules of inference and different proof techniques. While we were developing this, we were taking some certain other assumptions for granted. In fact, all the math that we do is built upon some series of axioms. And an axiom is just a statement which we sort of collectively agree to be self-evidently true. That's what an axiom is. Statements which we agree to be self-evidently true. So statements that don't require proof. We're just going to sort of all just agree that this is a true thing without actually proving it. Now, this chosen axiomatic system is going to be the basis that we use to establish, first of all, that sets even exists, and then to prove things about those sets, right, to prove certain statements within that system. And it's worth pointing out that the axioms that you choose to accept is going to have an impact on what you're able to prove, right? So if you sort of assume more axioms, you're maybe able to prove more things, but in some ways that also limits you because, you have to sort of follow the rule of whatever that axiom was. In fact, there's an entire area of logic which gets at the idea of which axioms are necessary and which axioms are sufficient in order to prove various important foundational mathematical theorems called reverse mathematics. But in any case, whatever axiomatic system that we're going to use, we want that system to be consistent. And a system of axioms is called consistent if it is impossible to prove that both a statement itself, let's call it P, and its negation of P, to be true, right? We don't want to be able to prove that P is true and also prove that the negation is true, right? We want the negation and the statement itself to have opposite truth values of each other. So we say that a system is consistent if it has no contradictions, right? If it's impossible to show that a statement and its negation are both true under that system. We also would hope that any system we use is called complete, and a system is called complete if every mathematical statement that you could possibly make has a truth value, and not just has a truth value, but is true or false. So a system is called complete if every mathematical statement can be proven either true or false. It doesn't mean has been proved true or false, but it's possible to find a proof to show that it's true or to show that the statement is false. Now, we would hope that any system that we use, any axiomatic system that we use, would be both consistent and complete. In fact, that's sort of what mathematicians were looking for, or even assuming that we already had for a very long time. Most mathematicians follow the Zermelo-Fraenkel axiomatic system. It's usually called ZF. Sometimes it's called ZFC if you add one extra axiom, which we'll discuss a little bit later. We're not going to discuss those axioms. We're not going to discuss them all very carefully because they're super technical, but the idea is that this set of axioms establishes a number of things that we all kind of agree to be reasonable, agree that these things are probably true. So the ZF axiomatic system establishes what it means for sets to be equal, It also establishes, it establishes that sets cannot be elements of themselves, which helps us avoid Russell's paradox that we've talked about in the past. It allows us to describe sets using set builder notations. That sets can be defined using set builder notation. It allows us to state that infinite sets exist. Infinite sets exist. And a few others. So I won't list them all here, but there's a few other axioms involved in the ZF system. Right, these are all sort of reasonable things, and while we often take them for granted and aren't really thinking about them when we're proving things, each one of them has important implications. Now, ZF is basically what most mathematicians use, and it's almost certainly a consistent system where you can't both prove a statement and its negation within that system. But the question is it a complete system? And as it turns out, the answer is no, and even more than that, ZF cannot be both consistent and complete, and in fact, there is no consistent system of axioms which is complete. So any consistent system that you come up with of axioms is guaranteed to be not complete. This was proven by a logician named Gödel. This is the first of two incompleteness theorems. He proved that for every consistent system, and we should be a little bit careful here. We'll say for every consistent system that can reasonably carry out arithmetic. So any consistent system that would be useful for us, right? We need our system to model, arithmetic in the natural numbers. That can reasonably carry out arithmetic. He proved that there is at least one mathematical statement which cannot be proven true and cannot be proven false within that system. Cannot be proven true nor false within the system, right, within the limitations of that axiomatic system. And a sort of shorthand way of saying that is that any reasonable, consistent system is not complete. By reasonable, I mean useful to us, right? Reasonable in that we can use it to sort of compute math the way that we understand it to be true. So any reasonable, consistent system of axioms is not complete. There's going to be some statement which you cannot prove and which you cannot disprove. And this, it seems a little unassuming when you just state it like this, but this was really like a huge bombshell proof of its time, and its time was less than 100 years ago. This happened relatively recently that Gödel came up with this proof in the history of mathematics. Mathematicians and logicians had been working for centuries to try and determine some sort of theory of everything, some axiomatic system, which was able to either prove or disprove every mathematical statement. This theorem tells us that not only have we not done that with ZF, it says it will never ever be able to do that. There is no consistent system that will allow us to either prove or disprove every statement. There's always going to be some statement which you cannot prove true and you cannot prove false, which was really kind of an earth-shattering thing that Gödel proved here. In fact, Gödel had another second incompleteness theorem, which explained why earlier when I said that ZF is probably consistent, this is why. So his second incompleteness theorem stated that in any reasonable consistent system, so for any consistent system that can reasonably carry out arithmetic, that system itself cannot prove its own consistency. That system of axioms cannot prove its own consistency. In other words, we can't just use the ZF axioms to prove that ZF is consistent. We can't use any set of axioms to prove that that exact set of axioms is consistent. So, why is that important, right? What are the implications? Well, for one thing, it shows that if we're working within some defined axiomatic system, like ZF or others, there's always going to be some statements that we'll never be able to prove and never be able to disprove. This is what we're going to call an undecidable statement. And again, undecidable is sort of a relative term relative to whatever axiomatic system that you're working in. We're usually working in ZF, right? But undecidable here just means within that particular system of axioms, there's no way to prove it and there's no way to disprove it. One such statement is something that we actually addressed in the warm-up problems, which we call the continuum hypothesis. So the continuum hypothesis is a statement that says that there is no set whose cardinality is strictly between the cardinality of the natural numbers and the cardinality of the real numbers. Right, cardinality of natural numbers and the cardinality of real numbers. We've proven that those two sets have different cardinalities. This is saying there is no infinity between the cardinality of the natural numbers and the cardinality of the reals, right? There's no set whose cardinality is greater than the natural numbers but less than the reals. And another way of saying that is to say that Aleph1, the first uncountable cardinal number, is the size of the real numbers. Is also the size of the power set of the natural numbers. So the continuum hypothesis is just that. It's a hypothesis. We don't know that it's true, although nobody's ever come up with a counterexample. Nobody's proven that it's true either. And Gödel, along with another mathematician, Cohen, actually proved that nobody's ever going to prove it one way or the other. The continuum hypothesis is actually undecidable in ZF, in the axiomatic system that we usually work in. So they proved that the continuum hypothesis is undecidable in the Zermelo-Fraenkel axiomatic system. So we're never going to prove it one way or the other. There's another, I think this is also Gödel, another important theorem which is undecidable is called the well-ordering theorem. So the well-ordering theorem, which is just a theorem that states that every set can be well-ordered. Every set can be well-ordered. Is also undecidable in Zermelo-Fraenkel and ZF. And if you're thinking, oh, didn't we give an example of a set that was not well-ordered, the integers? What the well-ordering theorem asserts is that given any particular set, you can come up with some well-ordering. It doesn't have to be the natural well-ordering. So the example that we had given in class was that the set of integers with its normal less than or equal to relation is not well-ordered. But that doesn't mean that the set of integers cannot be well-ordered. We can come up with a new relation. Z can be well-ordered. For instance, if we define a new relation, I'm going to give it a different name. I'm going to call it less than or equal to with like a little squiggle on it. Instead of straight lines, I'm using squiggly lines. We can define this relation on the integers by saying 0 is the smallest, and that's going to be less than or equal to -1, and that's going to be less than or equal to +1, less than or equal to -2, less than or equal to +2, and so on. So this ordering is a well ordering on the integers. It's not our standard ordering that we would use, but the integers can be well ordered. The well ordering theorem states that every set can be well ordered. Given any particular set, you can come up with a well ordering on it. And it turns out that the well ordering theorem, which shouldn't really be called a theorem at all, it should really probably be called a hypothesis, it's undecidable in ZF as well. There's no way to prove that it's true. There's no way to prove that it's false using the ZF axiomatic system. Now, this is just a couple of examples of undecidable problems, but what this means is that we're not ever going to be able to prove that they're true or they're not using any system, or using ZF, and probably using a lot of other systems as well. Now, some areas of math will then just decide, if the continuum hypothesis seems reasonable, they'll just decide to add in the continuum hypothesis as an axiom. They'll say, we're going to assume this is true, and we're going to be able to use the continuum hypothesis to prove other things as though it's true. Or more frequently, they'll use the well ordering theorem, and they'll assume that it's true as an axiom. But as we'll see when we start working through the exercises, sometimes if we decide to add an undecidable problem and just take it as an axiom, it can have some consequences that are really surprising and confusing, as we'll see.